outward, and then that would give sort of a combination of compression and extension. You'd have to look at the stress that would result to figure out what that is, but it's certainly a straining mode. But it appears that there's no possible way to represent any of the three required rigid body modes. Remember that this element would have to have translation in the x direction, in the y, and then rotation. And I think if you play around with those degrees of freedom, you'll see there's no way to add those up to get the required rigid body modes. Another problem area for this element would be passing the patch test. If you have an assembly such as shown here and you impose the constant strain field on it by moving the outer boundaries, you'd find that really the elements would lock up, and there's no way to get, for instance, in some interior element, a constant strain field. So just the assembly alone would fail there, which we mentioned earlier. Now, there's a paradox for the element developer that if you want to have a triangle in 2 dimensions, Zienkiewicz says that you must represent all 3 rigid body modes, and then you also must represent all 3 constant strain modes. Now, that will, in fact, take 6 degrees of freedom at least. And so, really, the Turner triangle is the simplest element that is a convergent element, and anything simpler, such as the one that we've proposed here, would fail. Problem 2 will test your understanding of the H convergence and the P convergence. I've created a hypothetical plane stress element that I'll call the amoeba element, and we will assume that there is a 6-noded version, a 10-noded, and a 15-noded version. Now, since this is plane stress, then each of those will have 2 degrees of freedom per node. And I want to set up a test case where we model a certain planar problem and use 100 of the 6-noded elements for one mesh, but use a second mesh with 49 of the 10-noded elements and a third mesh with 16 of the 15-noded elements. So we're playing off one against the other on P and H convergence. And the question is, which of those models will have the least error in stress? And we'll assume that the quality of the mesh in each case is similar. In other words, one of them isn't very badly done with a lot of distortion and a lot of the elements all bunched up in one corner. If you cast this into non-dimensional form, it could help a bit in the error comparison. To solve this problem, we need to know something about the polynomial nature of the interpolation functions, and then we need to know something about the average element size. We'll start with the polynomial discussion, and for a 6-noded element, there will be 6 coefficients required to define the u displacement, as well as 6 more for the v displacement. If we concentrate on the u displacement, we would need such a polynomial with 6 generalized coordinates, and that luckily turns out to be a complete quadratic. The 10-noded element will require 10 generalized coefficients, and if you lay those out, you find that you can do that with a complete cubic. Lastly, the 15-noded element, if you put all the 15 generalized coordinates out, will turn out to be a complete quartic. Now, as you can see, I've conditioned this problem a priori to give us rather nice functional behavior here. So whoever developed the interior workings of the amoeba element would undoubtedly use a complete quadratic, cubic, and quartic in that development. Now we need to think about the average element size. This is a 2-dimensional problem, and there are 3 models of the same geometry. If we think just in our minds of a square region, then the size of the element is going to be proportional to the square root of the number of elements. That's because we need to, in our model, we need to build our mesh in 2 directions. And so therefore, I'm going to use in the estimate for error, I'm going to not worry about the dimensions on this, but I'm going to say the error is proportional to here was the h value, which is proportional to 1 over the square root of the number of elements, which would be the square root of 100. The first model used quadratic elements and a lot of them, and that number comes out to be 1/100th. The second model used 10 noted elements. There were 49 of them, and the average mesh size or element size would be 1 over the square root of 49 in a non-dimensional way, with the complete cubic polynomial, and that gives 1 over 343. Lastly, the 15 noted element, the h is proportional to 1 over the square root of the number of elements, which was 16, and that was a quartic polynomial. That number comes out, this one, 1 over 256. So the winner is the intermediate complexity element and the intermediate mesh size. And so I think I contrived this ahead of time to keep people from guessing which one was going to win. And we had a pretty tight race between P and H convergence. And in this case, neither one won.